Hello, everyone. My name is Pierros Ntelis, and in this conference, I'm going to talk about advanced mathematical frameworks in cosmology. I would like to take the opportunity to thank the organizers from Cosmology from Home for giving me this opportunity to present my work in this international environment. So in this talk, I will try to argue that from all these different theories that we have, we can advance our mathematical modeling in order to address cosmological observations. And we're going to do that using advanced tensor theories and dynamical analysis in cosmology. Now, my short outline is the following. We have finished with the introduction. Then I'm going to talk about the theoretical framework behind all those different cosmological models. Then I will talk about the functor of action theories, FAT for short. Then a little bit about the quintessence. Then I'm going to talk about dynamical analysis in cosmology, then advanced tensor theories, and finally I will conclude and give some outlook. So let's start with the theoretical framework. Now, in cosmology, we talk about cosmological gravitology. And in the heart of those theories, there's the general relativity, which is the unique theory of a massless graviton. And all the systems in cosmology are modeled with this equation that you can see in blue, which is the action which models the geometry and the energy content of the universe. Now, if we would like to expand those theories, either we break assumptions, we add a field, or we introduce massive gravity. The most popular ones are introducing additional field, and therefore we can either add a scalar, vector, or a tensor. And the most popular ones are the scalar ones, and a generalization happened by Hordensky, which model a lot of different modelings that was out there, including the quintessence model, which is a hot topic these days. Now, there are also beyond Hordensky theories that are modeling the geometrical part with some scalar field. Now, from breaking the assumptions, we can either introduce breaking the isotropy homogeneity, locality, or causality, or add extra dimensions, or add probabilistic dimensions. Furthermore, we can discuss the non-Riemannian geometries, which are basically f of Rn types, curvature types, torsion types, non-metricity types, or a combination of those. And these are parts of metric affine gravity models. Now, in a study, we want beyond that, and we talk about functor of action theories, or FATs, if you will, and how these are working. Basically, from the action that you see on the left side, all the geometrical aspects or breaking the assumption is happening to this part of the equation. And then if we add the field, scalar one, tensor one, or massive ones, we change the Lagrangian aspect of the equation. Now, to go beyond that, we can consider functions or mathematical objects applied to the action itself. And this is how we build the functor of action theories. So in this framework, the FAT one, what we try to model is the following. Imagine that you have a cat that tries to pass through a room, which is the entrance and the exit, and it can take n paths to do that. Let's assume it's only two. Now, in a distant room, the same cat in the same room, but the room has slightly different structure that has some object that blocks the paths. We cannot have all the paths there. So we have less paths. Therefore, the action that tells us the number of paths on the left side is different from the number of paths on the right side. Therefore, there is a fluctuation of the action. And therefore, we can model the following. So the functor is the generalization concept of a functional, and functional is the generalization concept of a function. Then the action in physics tells us is the product of energy with time, and tells us the amount of possible ways a particle can travel from one point to another within a certain region. Therefore, the functor of function theories predict the existence of axionic fluctuation and field particles, which is an analog of the energetic topological fluctuation and field particles in nature. Therefore, we can build several mathematical objects on top of the action, and we can define a set of FATs, or a category of FATs. Now, a simple mathematical framework is that we can consider the Ricci action, SR, and a functional on top of this SR, plus some the action of matter itself. And we can build model on this direction as well. Now, in quintessence, we can discuss the following. The basic framework of quintessence is based on the standard cosmology, where we still have 1% baryonic matter and 31% of cold dark matter. And the dark energy, which is 68%, becomes dynamical now. And to do that, we need the cosmological constant, which is the potential of this phi field, and we need also a phi field itself. And when we put them together, we build the ϕ-CDM model, which is a model for quintessence. Now let's see how this works. In the standard cosmology, dark energy is constant and it doesn't move, doesn't have any dynamics, while the galaxy and cold dark matter are expanding with the expansion of the universe. Now, in the quintessence model, the ϕ-CDM model, the dynamics of dark energy change. And you see here a kind of an oscillatory pattern of dark energy denoted with red. And this is due to the phi quintessence field. While the galaxies and the cold dark matter are expanding, the dark energy has some kind of oscillatory oscillation. And now we still have observational and theoretical efforts in order to identify this rate of oscillations of dark energy. Now, stay tuned. Jackson and I have done several studies on that. We have explored ϕCDM model dynamics, simple ϕ-CDM dynamics, and analytical applications of the quintessence, along with the polyλCDM model that I discussed below. Now, in dynamical analysis cosmology, we discuss the dynamics using the phase space portraits, and you see here the description of omega matter as a function of omega radiation. So there are these points appear: an unstable point, a saddle point, which is attractor and repeller, and a stable point, which is an attractor. And the 0,0 is the dark energy one. Now, we can start from a repeller, which is radiation domination, and go to an attractor repeller, which is matter. And then from matter, we can go to dark energy. Therefore, we have those distinct epochs in our universe where we start with omega radiation, then we have the omega matter as dominant, and then we have the omega lambda dark energy dominance in the far future. Now, we have several epochs of redshift, matter radiation equality, cosmological constant and radiation equality, and matter and dark energy equality. And today, of course, we observe these values using a large-scale structure surveys. Now, we explore ϕCDM model dynamics in the standard way, and this introduced many variables and parameters, rich in phenomenology, highly chaotic, and there are a lot of numerics involved. Now, is there a simpler way to model ϕ-CDM dynamics? And the answer turns out to be yes. And we have introduced the simple ϕ-CDM dynamics. And to do that, we explore the same dimensional variables as before for matter and radiation. However, the kinetic energy density is built exactly as proportional to the kinetic phi dot square instead of phi dot. And the potential term is also V instead of square root of V. And by having these dimensional variables, we build simple modified Friedmann equations along with the continuity equations, which are easy to solve numerically and analytically, it turns out. And there's no need for lambda and gamma parameterization, which were needed before in order to model specific potentials for the quintessence. Therefore, our modeling is generic one, and it can be introduced to different kind of potentials. Now, you see, if we make a comparison between the ϕ-CDM and a lambda-CDM, the differences are very insignificant, and when it is important is at the late time universe. So this builds a simple quintessence model which is applicable at the late time universe. Now we have done stability analysis and we have characterized the critical points of this analysis, and you see we have an unstable radiation domination, an unstable matter domination, and a stable scalar potential domination in the far future. Now let's go to a further study. We asked ourselves, is there an effective model to distinguish among different modified gravity cosmological models? And it turns out the answer is yes. And we have built this analytical polyλCDM dynamics and the polyλCDM model. And how did we build that? We have used an action with effective Lagrangians, which model modified gravity models. And you see here, we have used the standard cosmological constant dark energy, matter, and radiation. And we have introduced Lagrangians for f of r, simple f of r interacting with a ϕ model, a curvature which looks like a scalar field, Lagrangian, a Lagrangian which is an interacting dark energy model, and a SVT, scalar vector tensor field for modified gravity models. Then we have used the standard dimensional variables S, which is for different species, omega S, and we have the standard Friedmann equation for this one. And then if we combine the second Friedmann equation and the continuity equations, we build a simplified dynamical system for each of the species. And we introduce different parameters A, S for the different Lagrangians that you see above. And it turns out that this system is solvable with analytical simple exponential solutions that you can see in the equation below. And then we can provide a dynamical analysis, which looks like that. And you see here on the left side, we have different domination epochs for different species of this Lagrangian. And for example, when we have matter domination, we can check in which plane this behaves as a saddle, reflector, or an attractor. It turns out it doesn't behave as a saddle at any plane, but in the plane, for example, dark energy and matter, it behaves as a reflector. Potential and matter, a reflector, and so on. While in the plane radiation and matter, it behaves as an attractor, or Z component and matter, it behaves as an attractor. Therefore, we conclude that we can find the global transition from Z component to the saddle reflector, dominant components, matter, radiation, curvature, and X, and then to the component V, which is an attractor saddle point, which in turn it is also transits to the final cosmological constant, which is an attractor epoch in the far future. Note that there is a subtle transition between the X component and the V component, and there is a subtle transition between the V and the lambda component in the far future. Now that we have discussed the dynamical analysis in cosmology, let's talk about advanced tensor theories. Now, in advanced tensor theories, we have introduced a generic tensor, which is simply the map between a generic combination of vectors V to the generic number set G, which is written in this symbolism. And this can introduce geometrical and topological interpretation using fractional derivatives. And you see here a manifold M, and at the point P, you can build the standard tangent manifold using the standard derivatives, or in green and blue, the fractional tangent manifolds using fractional derivatives. To discuss that in simpler terms is that in the literature there are tensors such as the following, where you have nu1 and nu2 indexed up and nu1 and nu2 indexed down. What do you notice? That these indices, they have each one of them its own index. Therefore, this is the new idea. We can define the index of the index of the index, and this builds a generic index, which is L, K of J of I. Now, this can build a generic tensor. Tensor L, K through Ji, alpha, beta through psi, omega. And therefore, we have built a new mathematical object, which is an advanced tensor. And this turns out to have several applications. For example, transformations. How should I transform a set of vectors non-linearly and non-locally according to a property of 2D space? And the answer is using these generic tensors. How do we do that? Basically, we fill the space with some scalar field, which is x squared. From the left have small values, to the right it has big values. We take a rectangle, blue, which is the original rectangle, and then we apply a transformation that looks like that. We take the u vector, for example, the 1, 1, and then we apply this generic tensor mu beta nu, then a partial derivative mu, and then a fractional partial derivative applied to this potential around this space. This can be either curvature or some energy or some potential on the space around. And when we do that, we take into account the property of the space in order to transform non-linearly and non-locally the blue rectangle into the rectangle. And therefore, what we have used to do that is the advanced tensor, T, mu, beta, and nu that you see on the definition above. Now, these frameworks have several applications. For example, tensors defined using fractional derivatives, transformation properties, geometrical and topological interpretation, and you can combine these generalized tensor theories with set theory and category theory. Now let's go to the conclusions. Basically, we have proven that there's a mathematical and observational evidence for functor of action theories and predictions of actionions, the quintessence modeling. Then we have applied dynamical analysis in standard cosmology, quintessence, and the polyΛCDM model framework. And then in advancing tensor theories, they introduce generic indices, generic tensors, and generic tensors connected with fractional derivatives. And these have plenty of applications in categories, sets, algebraic geometry, topology, diffusion, cosmology, statistics, and artificial intelligence. So I would like to thank you for your attention, and I'm looking forward to discuss these ideas with you. Bye-bye for now.